Hello, good evening, everyone. Okay, so for today's class, basically, we have one. So basically, we are nearing the end. Correct? We're already in week 10. Okay, so there are basically two major topics to complete. All right, for the module. So one we're going to cover today, which is on the scheduling theory, and the other one which we'll cover next week, which is virtual memory. Okay. So for today, we will cover the topic on the scheduling theory, and after that, I will spend some time again discussing the term paper and then the assignment too. Okay, so I've received some queries over the week, okay, about both of these submissions. So I will try to clarify and explain again how to approach them and the common questions that I'm receiving. Okay, so let's get started. Okay, on the scheduling analysis. Okay, yeah, and towards the end of the lecture, I'll also talk about the exam. All right, so you are aware of the plan. Okay, so let's go ahead to start discussing. Okay, so of course, over the weeks, it's natural that the attendance for the actual class goes down, but I do believe that everybody is watching the lectures or the recordings after that. All right, so if you attend the class, of course, it is good. It's easier that way. All right, but if you are unable to attend, okay, do make sure you watch the recordings at your time, at your free time, okay, so that you catch up with the class. Okay, so in this chapter on scheduling, we are basically going to cover the theoretical concepts of scheduling theory, okay, and how we analyze a multi-threaded system in terms of the timing, the deadline, and things like that. Okay, so before we go into that, let's just have a quick review. So we know that in terms of any task, okay, when we first create the task, it will go into this state called the ready state. Okay, so this ready state task will actually form a queue. Okay, depending on the priority. Okay, so there will be a queue. Okay, where there will be many tasks, and the task that is highest priority will be the top of the queue, followed by the rest of the tasks. Okay, and the scheduler. Okay, the scheduler will have to determine the highest priority task from the queue and allow that task to transition to the run state. Okay, so when a task is running, of course, as we have seen before, events like semaphore, mutex, message queue task, all of these things, when you try to do them, okay, when you try to execute OS call, kernel call, and if it's successful, you can carry on running. Okay, but if it is not successful, then you end up going into what you call a block state. Okay, so if I try to lock a mutex, acquire a semaphore, and it's not available, all right, then I will go to a block state. So when I go to a block state, then of course, automatically what happens is the scheduler comes in again to select the next person in the queue to take over the CPU. All right, and when you're in the block state, when the event or whatever the resource you're waiting for becomes available, then you get unblocked, okay, and then you move on to the next stage, which is you go to the ready state, and then once you're in the ready state, if you're higher priority, you again go to the top of the queue. Okay, and this sort of sequence goes indefinitely. So this cycle between ready, block, and running goes on indefinitely within the system while your system is still running. Okay, so that is the general idea, and we have already seen this sort of happening in the last two lectures, right, when we looked at the various OS kernel calls and what happens, and we drew the state transition diagram. Okay, so that sort of gives you a clear idea of what is really happening in the back end, okay, when you see the output coming out. Now, in terms of scheduling algorithm, okay, what we want is how do you ensure, or how do you come up with the policy of allocating priorities, okay, to the various tasks, okay. And of course, the main objective you want to fulfill is that all the tasks must meet their respective deadline. All right, that is the whole idea of a system. All right, you want to be able to meet your deadline. Now let's look at a simple example first, where you have 3 tasks. Okay, so of course, we must understand that when we do in this lecture, we are looking at it from a very theoretical perspective. All right, in reality, many of some of these assumptions may not hold true. Okay, so we take it that this is a theoretical analysis, and of course, when you apply it to a practical scenario, some of this may hold true, some may not hold true. Okay, so the first sort of assumption that we are going to hold when we look at this whole topic is that at a particular time t equals to 0, we assume that all tasks are ready to run. Okay, all tasks are ready to run at the time t equals to 0. So let's look at this 3 tasks A, B, and C. Okay, so we have 3 tasks with 3 different execution time and 3 different deadlines. Okay, and what we want is we want to look at how can I schedule these 3 tasks. Okay, so let's assume that I go in this order A, B, and C. Okay, so like I said, all tasks are ready at time t equals to 0. That means at time t equals to 0, give me a minute. Yeah, so at time t equals to 0, we say that all the tasks are ready. That means they all want to use the processor. So if that is the case, and I go in this sequence A, B, and C, let's see what happens. Okay, so the first instance will be at time t equals to 0. So this is t equals to 0. So A will run first, since I'm going in this order A, B, and C. So A will run first. A has a execution time of 10 milliseconds. Okay, so we will assume that one block here. Okay, so whenever I see one block, that is considered 10 milliseconds. So after 10 milliseconds has passed, A is complete, and then I can run B, and B will take 20 milliseconds. Okay, after that I will run C. So that is the sequence. Now let's look at the deadlines. So the deadline, okay, for the 3 of them are given here. So let's see the deadline. So for the deadline for A is 50 milliseconds. So A meets the deadline. Correct. So within the first 10 milliseconds, I already complete. So it's fine. Okay, but what about B? The deadline for B was 20 milliseconds. But B only completed at the 30 millisecond mark. So B actually missed the deadline. Okay, for C, the deadline was 60 milliseconds and I complete within 60 milliseconds here. So it's no problem. So A and C, no problem. I was able to meet the deadline, but B, I missed the deadline. Okay, so we can see that this order of A, B, and C is not going to work for us. How about I switch it around? So since I know that B missed the deadline, why don't I put B, A, and C? Okay, so I'll run B first, followed by A, followed by C. Okay, and if I look at the deadlines, you can see that all the tasks meet the deadline, because for B by 20 milliseconds, I'm able to fulfill and complete task B. By 30 milliseconds, I actually complete A, and by 60 milliseconds, I complete C. Okay, so the execution time is the amount of time you need to execute the code, okay, associated with that task. The deadline is the sort of final time by which you must complete. The duration is the execution time. Okay, the duration is the execution time. That means the time that I need to complete that particular task. Of course, here again, this assumption is there are no preemptions. Okay, that means when I run task A, I will run task A without getting preempted and so on. Okay, so it is just the idea of again, one assumption for this first example here. Okay, so let's flip it again and we change the order a bit, say B, C, A. Okay, so if I run B first, then C, then A, then what happens? Okay, so you can see that B missed the deadline. Okay, I fulfill by 20 milliseconds. Okay, C also I complete by 60 milliseconds. Okay, because by 50 milliseconds I already complete. But A, I miss the deadline because A only starts in the end. So A only starts at 50 milliseconds and finishes by 60 milliseconds. So I miss the deadline for A. Okay, so you can see that when we try randomly, okay, one of it happens to work, okay, but the rest fail. Okay, so of course this is just to show you the idea that, okay, if I just randomly try, you may come across one that works. Okay, but of course that is not an ideal way of deciding the order of execution. Okay, so one of the assumptions or one of the terms we need to first understand is, of course, what exactly is the concept of this period and periodic nature of tasks. Okay, so if you remember that when we looked at our code, the semaphore code, everything, all our code, so even though we have a task A, task B, whatever, okay, eventually everything is written inside a while one loop. Correct, the task. So we take the concept that every task is written to run indefinitely. Okay, so with that understanding, we say that there is a sort of periodic nature of tasks. Okay, that means every task will repeat itself at every periodic instance, and every time it repeats itself, it will run. Okay, but each time it runs, it may have a different set of parameters, which means that the actual execution time may change. Correct, because maybe at this particular instance, the if else took the if, then another time it took the else. Correct, and then maybe another time the loop ran for a bit longer or a bit shorter and so on. So even though it's the same task running, each instance may have a slightly different timing characteristic. Okay, so in that with that understanding, we can say that we assume the worst case execution time for a task. Okay, that means if I have different ways of executing a particular task, what is the worst case execution time? So that is the parameter we're interested in, okay, when we are trying to do this analysis. Okay, now the other parameter is this concept of the deadline, correct? Because we know that the deadline is the worst case timing by which I must have completed. And since we know that the tasks are periodic in nature, okay, we can say that the worst case execution time C must be lesser than or equal to the deadline, and the deadline must also be lesser than or equal to the period. Okay, so to make it simpler, we just say that the deadline is actually the same as the period. Okay, why? Because we come back to the same understanding that the tasks are already periodic in nature. So the deadline is the period. So as long as I complete before the next iteration of the period, then I'm fine. All right, so that is the second sort of assumption or understanding. Okay, and of course, some other additional assumptions. Tasks are completely independent of each other. So we do not consider the case where one task depends on another task and so on. And we do not factor in any other additional overhead. Okay, so we know that whenever a task switches from A to B and B to A and so on, there is always this pushing of contacts, pulling of contacts, this contact switch time. So we do not factor in all this time. Okay, so we say these are negligible. Okay, so this is just to help us have an easier way of analyzing the behavior of the task. Okay, so the next thing is the worst case. So we saw the worst case execution time. Now, what is the worst case response time? Worst case response time is basically the same as worst case execution time, except that you are including the concept of interference. So without any interference, okay, or in other words, preemption, correct? Then we say it's worst case execution time. With preemption, then we say it's worst case response time. Okay, so when we say preemption means the concept that another task will come in to interfere with your current task, and then because of that, your current task needs more time to complete. Okay, so example over here. Okay, so originally you only took this amount of time. Okay, but because of the interference, that means the preemption, you now take more time. Okay, so that is the other term that you must be familiar with. Worst case execution time and worst case response time. Okay, so of course, when you have interference, there is a higher chance that you will miss the deadline. There is a higher chance that you will miss the deadline. Okay, as can be shown here. Okay, where there is a task Y interfering with task 1, and then because of that, you miss the deadline. Okay, so of course, the idea of this preemption exists because we are talking about a preemptive priority driven scheduling algorithm. Right? That means when you say preemptive, the very nature is that a higher priority task will automatically take over the CPU, okay, from a lower priority task, okay, once it is ready. So that concept is that. All right, so that is why the preemptive priority driven scheduling actually is helping us in a sense that it ensures that a higher priority task will always be able to take over the CPU and complete. So let's look at how such a system could work. Okay, so we already saw this actually again in the last demo last week. All right, but we will see this again. Okay, so now I have 3 tasks, T1, T2, and T3. So task 1 is high priority, task 2 is medium priority, and task 3 is low priority. Okay, so if I look at this sequence, since let's assume that at time t equals 0, only task 2 is ready. So even though I have task 1 and task 3, but at time t equals 0, only task 2 is ready, so task 2 will run. So while task 2 is running, if suddenly task 1 becomes ready. So since task 1 is considered a higher priority, okay, it will automatically preempt task 2 and take over the CPU. Okay, and then it will run. So once it starts to run, it will run until it completes or it gets blocked. Okay, so at that point of time, okay, if while task 1 is running, task 3 gets ready, task 3 has to wait because task 3 is a low priority task. Okay, so even though task 3 may be ready at time t equals to 18, it still has to wait. Okay, when task 1, so at this point of time, what happens? So task 1 has given up the CPU for task 2 to run. So maybe task 1 got blocked. Okay, you wanted to acquire a resource but not available. So it gets blocked. So it allows task 2 to run. Okay, and eventually when task 2 gives up the CPU, then task 3 will be able to run. Okay, so that is the whole idea of preemptive priority driven scheduling. Right, the highest priority task will always take over the CPU and run. Okay, so with this concept, of course, comes back to another important thing. Right? How do I assign priorities? So since I know that a higher priority task is always going to take over, how do I assign priorities? Okay, so with this, there are 2 possibilities. One is fixed priority and the other is dynamic priority. So when I say fixed priority means once I create a task, okay, like how in our demo we looked at the app config.h, okay, when we went to the setting to change the priority level. So we can have a fixed priority. So once you create a task with a particular priority, it stays that way. Or the other one is dynamic priority, okay, where the priority changes with time. Okay, so one of the most popular algorithms, okay, used in scheduling analysis is what we call the RMS, okay, rate monotonic scheduling. Okay, and it's widely used and accepted sort of standard of analyzing the scheduling of a multi-threaded system, and it works on the idea of having a fixed priority in periodic tasks. Okay, so again, this is the assumption that every task is periodic in nature, so we assign fixed priorities, okay, based on the periodic nature of tasks. And the idea is very simple. Priority is inversely proportional to task period. Okay, why is this so? Because when the task period is short, that means if I say that I have 2 tasks, task 1, this is the periodic interval, and I have task 2, longer periodic interval. Okay. Then if task 1 is a shorter periodic interval, that means it is repeating itself a lot faster. Okay, if it's repeating itself a lot faster, which it means that it needs more immediate attention from the processor to complete its task before the next periodic interval kicks in, compared to task 2 where it has more time to complete, so it can afford to wait a bit longer. Okay, so with that simple sort of very basic thinking, we follow this rule that says that priority is inversely proportional to task period. So when I have a task that has a shorter period, it implies a higher priority. Okay, and if it's a longer period, then it's a lower priority. So let's look at a simple example here. So I have two tasks, task 1, task 2, and task 3. Okay, so if you see down here, you can see that in terms of the period, okay, which is the same as the deadline, task 2 has the shortest period. So this is considered the highest priority. Okay, followed by task 1, medium priority, and task 3, which is the lowest priority. Okay, so we are going to use the RMS rule, correct, and assign the priority. So since task 2 is having the highest priority, okay, we are going to go ahead to run task 2 first. Okay, so task 2 will run first. Okay, after task 2 runs for 1 unit of time, then it is able to free up the CPU, correct, and then the task 1 can take over. So task 1 takes 2 units of time. So the C here is the computation blocks or units of time that you require. So task 1 will take 2 units of time. After task 1 is complete, okay, there is no other instance of task 1 and task 2, so we will allow task 3 to run. So when task 3 runs, as you can see, task 3 requires 2 units of time to complete. Okay, but the moment it completes 1 unit, okay, the next periodic interval of task 4 kicks in. Sorry, task 2 kicks in at time t equals to 4. Okay, so since that next interval kicks in for a higher priority task, automatically I will switch. So I'll get preempted and I will switch to task 2. So after task 2 runs, okay, since task 2 only requires 1 unit of time, then I will run task 1. Okay, and then after that, I will be free, and then I will be able to run the second unit of computation for task 3. So task 3 will complete, but it will have to be preempted and then it will come back later. Okay, again at time t equals to 8, the third periodic interval of task 2 runs. Okay, and after that, what happens? There is a period of time where there's no task running. So you can see that because of the periodic nature, there is this block of time over here where there is no task running. Okay, because task 3 has completed, task 2 also completed, and task 1 only comes in at time t equals to 10. So there is a block here, there is no time, no task running, and at time t equals to 10, the next interval of task 1 kicks in and it runs. Okay, then again task 2, okay, and then after that we wait until the next interval of task 1. But in the next interval of task 1 at time t equals to 15, what happens? Okay, it runs 1 block, but before it can finish, there's the fourth periodic interval of task 2 starts. So that means I need to get preempted again and run to task 2. After I finish, I will come back to task 1 to complete. Okay, and then what happens? I'll wait until time t equals to 20, and then the whole sequence repeats. So if you look at time t equals to 20, you will see that from time t equals to 20, it is actually the same as time t equals to 0, because all the tasks have completed and you are starting again from fresh, because at time t equals to 20, a new instance of T1, T2, T3 all will want to be launched at the same time, similar to time t equals to 0. Okay, so time t equals to 20 onwards, for the next 20 cycles, you will have the exact same behavior as time t equals to 0. Okay, so that is the concept of what we call the hyper period. Okay, so if you look at a hyper period, okay, and you can see that everything is schedulable, then that whole sequence is what will repeat itself again and again, okay, throughout the next hyper period, and so on. So this hyper period, how do you calculate? Okay, it's very simple. It's just the least common multiple of the task periods. Okay, so if I have 3 tasks, which is 4, 5, and 10, I just look at the least common multiple and I'll get 20. So that means that the 20-second mark is the hyper period of the task set that we have. Okay, and once I simulate my behavior throughout this hyper period and I do not miss any deadline. Okay, so if you come back here, you can see that I did not miss any deadline. Yes, preemption occurred, but it was fine. Okay, I get preempted, but I'm able to come back and I'm still able to finish before the deadline. Correct. So in that sense, I did not miss any deadlines at all. So if I'm able to look at the behavior, analyze the behavior of the task set within one hyper period, and I do not see any deadline being missed, then I can say that the task set is schedulable. Okay, the task set is schedulable. Okay, of course, it is not so ideal, right, to keep drawing all these blocks for so many different tasks and trying to analyze. Okay, so of course, we want to have a more easier, more mathematical way of understanding this. Okay, so that is where the next part comes in. So we're going to look at the concept of the feasible schedule and optimal scheduling algorithm. Okay, so what is the feasible schedule? Is basically a schedule that can meet all the timing constraints, and a optimal scheduling algorithm is one that produces a feasible schedule if it exists. Okay, so why we say if it exists? Because you could have an instance, okay, we will see in a while, where you are not able to fulfill the deadlines. Okay, you try to do too many things, all right, or you have too short deadlines for many tasks and you're not able to fulfill the deadlines. All right, so optimal scheduling algorithm may not exist. Okay, and one of the things about RMS is, if you try RMS, okay, if you do not try RMS and you just arbitrarily use some fixed priority assignment for the task that you have. Okay, take for example, I have 3 tasks. Okay, task 1, task 2, task 3, and task 1, task 2, and task 3. Okay, and I just randomly try to go through all the different possible scenarios. Okay, so for n tasks, I have n factorial different permutations. Okay, if I try to go through all of these permutations and I take for example, I draw out this hyper period. Okay, what I will see is, if there is a possibility that you have any of this combination that actually works, that means it's a feasible schedule. Okay, when we say feasible schedule, means you are able to meet the deadlines. Okay, then it is guaranteed that RMS would be one of them. Okay, so what we are trying to say is that if I even randomly just try to assign and try to figure out the different ways in which I can allocate the priority of the task. Okay, and in this example, let's say I find 2 possible scenarios, okay, where I'm able to fulfill the timing deadline. What the theory says is that RMS will definitely be one of them. Okay, so since we know the RMS is always guaranteed to pick a feasible schedule if it exists, we don't need to waste time trying all sorts of combinations. We can straight away go and try RMS first to see whether such a possibility exists. Okay, so to do RMS, okay, how can we do it? Correct. So just now we saw, of course, the sort of pictorial way. Right, you understand the concept and then you draw out a timing analysis. Okay, and which time slot, what happens, and so on. All right. So of course that is one way, but now we're going to look at it from the analysis, the schedulability analysis. And what we want to do is we want to analyze the system based on its worst case behavior and see whether it's able to fulfill the timing constraints. And how can we do that? So the first thing that we need to compute is what we call the utilization. So this utilization is basically a measure of how much of the processor time are you using. Okay, because you have a single processor and you're trying to spread that processor across all the different tasks that you have. Okay, so what we need to do is we need to see whether you have enough processing power to be able to spread out across all that you want to do. Okay, and to compute this utilization, you just follow this formula, which is the summation of C over P, which is the computation time of the task over the period of the task. Okay, so in this case, it is 2 over 5 for the first task, 1 over 4 for the second task, and 2 over 20 for the third task. All right, so you get a value of 0.75. So how do I interpret this value? Okay, as long as the utilization is less than or equal to 1, then you say that that is a necessary condition for any task set to a feasible schedule. Okay, so this utilization means that you are using the processor in a way that there is enough of processing power to go around for all the various tasks that you want to complete. Okay, but the moment you say that u equals less than equals to 1 is not satisfied, then you can say it is not schedulable at all. Okay, so this is what we call a necessary condition, but it is not a sufficient condition. Okay, so there is a difference here, so you must be careful of the terms that we use. So what is necessary, what is sufficient? Okay, sufficient means it is enough. Okay, when you say it is enough means once I satisfy the criteria, I can guarantee that I am able to schedule all the tasks within the deadline. Okay, but what the theory says is u less than equals to 1 is necessary. Okay, why is it necessary? Because this 1 represents the 100% of the CPU time. Correct. So if I'm using up to 100%, then it makes sense that it is possible. Okay, it is possible that I'm able to do what I want to do. But the moment the utilization is greater than 1, that means you don't have enough processing power already. Okay, to do all that you want to do. Okay, so this is necessary. Okay, so as a bare minimum, this is necessary. But just because it is less than or equal to 1 doesn't mean you can guarantee a feasible schedule. It is not guaranteed. Okay, so sufficient means it is enough, but u less than equals to 1 is not enough to say that a feasible schedule exists. Okay, it's not enough to say that a feasible schedule exists. Okay, so just to demonstrate what we mean, okay, so you can see this example here where I have two tasks, task 1 and task 2. And if you look at the utilization, okay, it will be okay 2 over 5 plus 4 over 7. Okay, it will give me 34 over 35, which is less than equal to 1. Correct. So in terms of the utilization, yes, it satisfies the utilization criteria. But if I were to analyze it, okay, by drawing out the timing diagram, okay, you will see that if I follow the RMS rule and I say task 1, since task 1 is a smaller period, it is a higher priority, so task 1 will run first, followed by task 2. Okay, then what happens is, since task 1 is a period of 5, when task 2 is running, before it can finish, task 2 will be preempted by task 1. Okay, and then only task 2 can run. Okay, but when task 2 runs the last block, it already passed the deadline. It already passed the deadline, so it is not feasible. And even if I try to switch it around and I say task 2 run first, okay, that means task 2, if I give task 2 higher priority, then it also comes in this another situation where task 1 will miss the deadline. Okay, so you can see this example that even though I satisfy the utilization requirement, okay, it is not sufficient. It is not enough to say that just because utilization is less than or equals to 1, I am able to guarantee that I can actually schedule them and meet all the deadlines. Okay. So that's why we say that a task set may or may not be schedulable. Okay. Even if U is less than or equals to 1. Okay. So what can we do? Okay. So of course, what we said is first we assign priorities using RMS. That's the first step. Then we look at the behavior over the whole hyper period, and we try to see if any deadline is missed. If no deadline is missed, then task set is schedulable. Okay. So of course, the first thing is we always check for this condition. The moment this condition fails, you don't need to do anything else already. Okay, you straight away can say that it is not schedulable. But once this is satisfied, then you can go and do these 3 steps to check whether the task set is schedulable under a fixed priority system. So let's look at this example here. So based on this understanding, all right. So the first thing is like what we did just now. Since I have 2 tasks, and just now we saw the utilization is 34/35. Correct, the same example. So since we know utilization is less than or equal to 1, which is satisfying the first criteria, then we go and do the steps, which is first I assign priority based on RMS. So based on RMS means the smaller period task will have a higher priority. So task 1 will run first, followed by task 2. And when I draw out the timing diagram, we can see that task 2 actually misses the deadline. And once we can see that this is happening, we can immediately say that this task set is not schedulable. Okay, so when we say not schedulable means that given the current timing constraints, it is not possible for us to fulfill the deadlines that we have set. Okay, so that is what it means by it's not schedulable. Okay, so of course, the next step is trying to compute everything based on the entire hyper period may not be feasible, correct? Especially if I have a large hyper period. Okay, imagine, okay, just now hyper period of 20 cycles is okay, still manageable to draw out and analyze. Okay, what is my hyper period is 500 cycles or 800 cycles. Okay, so it's not feasible to analyze it, okay, in such a large hyper period. So that is where we have another condition where this other formula called a utilization bound. Okay, so what is utilization bound? So utilization bound is given by this formula over here. Okay, so you don't need to worry about the formula, you just look at the table in the next page. Okay, so this utilization bound, basically what we need to do is we compute the utilization and we check whether it is within this utilization bound. All right, but the interesting thing is this utilization bound is not a necessary condition, but it is a sufficient condition. Okay, so what does that mean? That means if I satisfy this, if I say I satisfy this, then I immediately can say it is schedulable. Okay, but even if I don't satisfy this, I may still be able to schedule them, okay, within the deadlines. Okay, so that is the sort of interesting thing about this. Okay, so the utilization bound number is a sufficient condition. That means if I meet this condition, yes, you can say you're definitely schedulable. But if I don't meet, doesn't mean you're not schedulable. You could still be schedulable. Okay, so this B1, 2, 3, 4, this is just basically n. So this means n is equals to 1 or n equals to 2 and so on. Okay, so all these values are already given here. Okay, so let's look at an example. Okay, so if I look at this 2 tasks over here, T1 and T2. Okay, so since I have 2 tasks, I need to look at this number, n equals to 2. All right, so the first thing I do is, of course, I say I compute utilization. So utilization will be 1/2 plus 1/3. And that will give me the value of 0.8 333. Okay, so that is the utilization value, and since this is less than equals to 1, then you can do the next step. Okay, so of course the next step, just now we said earlier, we try to draw out hyper period based on the RMS. Okay, but now let's look at the other step, which is computing and calculating the utilization bound. So since we know the utilization bound is 0.828, we can see that the U is actually lesser. Is actually the U is actually greater than the bound. Okay, the U is greater than the bound. Okay, but just because the U is greater than the bound doesn't mean that it's not schedulable, because if I were to draw out the timing diagram, you can see that for task 1, the deadline is 2 units, which is here, and for task 2, the deadline is 3 units, which is here. Okay, so at time t equals to 0, if I were to start, T1 will run first, followed by T2, and then when the next instance comes, T1 will run, and then the T2 will run, but I will not miss any deadline because task 1's deadline is here. So this is 2 units. Task 2's deadline is here, 3. Okay, so I do not miss any deadlines, and I'm still able to schedule according to the RMS. That means the lower period task has a higher priority. Okay, so it tells you that the utilization bound calculation is sufficient, but it's not necessary. That means even if I don't satisfy this check, I may still be schedulable using RMS. Okay, so this sort of gives you a nice summary, okay, of the various things. So the first thing is, of course, utilization greater than 1. The utilization greater than 1 already we know is not schedulable, so we do not need to check anything else. Okay, but utilization less than or equal to 1 is necessary. So this is the bare minimum we need to ensure that it may or may not be schedulable. Okay, so of course, when you say may or may not, then you still have other things, which is the RMS, okay, and then the hyper period. Okay, to guarantee that it's schedulable is when I fulfill this condition. Okay, if I fulfill this condition, then we say it's sufficient, then it is definitely schedulable. You don't need to think already. Okay, that is definitely schedulable. Okay, so let's look at the schedulability analysis. Okay, for tasks that meet the necessary condition but not the sufficient. Okay, so the necessary condition is what? Necessary condition is the U less than or equal to 1. Sufficient condition is the U less than the utilization bound. Okay, so U less than or equal to the utilization bound is the sufficient condition. The necessary condition is U less than or equal to 1. Okay, so let's look at how we can proceed with this. Okay, so if I look at these 3 tasks over here, T1, T2, and T3, okay, what do you see? You see that when I look at these 3 tasks, task 1, okay, has a period of 100, task 2 will be 150, and task 3 will be 350. So task 1 is higher priority, followed by task 2, followed by task 3. Okay, now for 3 tasks, n is equals to 3, so I need to look at this utilization bound. Okay, because n is 3 tasks. If I compute the utilization, so this utilization 0.952, how you get? Okay, is 40 over 100 plus 40 over 150 plus 100 over 350. So you'll get 0.952. Okay, so you can see that this utilization is already greater than the bound. So it does not meet a sufficient condition. It does not meet a sufficient condition, but it is lesser than equals to 1. So it fulfills the necessary condition. Okay, it fulfills necessary condition, but not a sufficient condition. So what can we do next? So the next thing is, let's look at it from one task at a time. So if I just consider task 1 alone, just task 1, that means I don't care about task 2 and task 3. Okay, the utilization is 0.4 and is less than the utilization bound of task 1. a utilization bound of 1. Okay, so it passed the utilization bound test. So if I just have task 1 alone, no problem. All right, only one task. What else? What if I add in task 2? So task 1 and task 2, the utilization is less than the utilization bound. So B2 is 0.828. So again, once your utilization is lesser than or equal to the utilization bound, you can straight away say that it's schedulable. Okay. Yeah, B1, B2, B3 all is given from the table. Okay, then the next is when I include the task tree. So when I include the task tree alone, then I know the utilization is bigger than the bound. Okay, so the utilization test fails. Okay, but again comes back to the thing that just because the utilization bound test fails, we can only say that it still may or may not be schedulable. Okay, so it still may be schedulable. We do not know yet. Okay, so how can we analyze this? Okay, so to have a better idea of this, we are going to look at this thing called the critical instance. Okay, so a critical instance of a task means it is a point of time where when you release the task, you also have all the other higher priority tasks also released at the same time, which means you have to wait the longest. All right, you have to wait the longest. So if I have multiple tasks, for example here, and all of them are released at the same time. So when I say release at the same time means you can just think of it as time t equals to 0. That means all the tasks are ready at the same time. So if that is the situation, what happens? That means I need to allow all the other higher priority tasks to run, and I must find for some gap in between to run my lowest priority task. Because all the higher priority tasks are having their own periodic interval and they're going to consume the CPU. So the lower priority tasks will need to now look at where it will find a gap to actually run and execute. Okay, so let's look at this. Okay, let's look at this and see the critical instance for task 3, because we know that because I included task 3, then the utilization bound test has failed. Okay, so how can I analyze this further? So if I look at this, you can see that since all the tasks are released at the same time, t equals to 0, okay, all the higher priority tasks P1 and P2 take up more CPU processing time because they're higher priority. So task 3 is not able to have enough time, okay, to complete. Okay, so in this worst case scenario, okay, what we want to do, we want to analyze it, okay, based on the computational demands of all the higher priority tasks, okay, which is the interference that the lowest priority task is facing. Okay, so let me show you the example. Okay, instead of going through all of this, I show you the example. I think you relate to it a lot easier. Now, if I look at this here, what do you see? You see that when all 3 tasks are released at the time t equals to 0, okay, task 1 has a periodic interval of 100. All right, so this is 1 interval, 2 interval, 3 interval, and the 4 interval. Okay, task 2 has a periodic interval of 150. So this is the first, the second, and then the third one. And similarly, task 3 has a periodic interval of 350. So this is the whole interval. Okay, so when you look at this, what do you see? You see that you have task 1, correct, and task 2, okay, interfering with task 3, correct? Because task 3 is the lowest priority task. So because you have 2 higher priority tasks, they are going to take up more CPU time, correct? That is why task 3 is impacted. Okay, so what I need to do now? Okay, so what are the steps involved? What we look at is when the timing deadline, okay, the timing deadline of the various tasks. So we know that the deadline for task 3 is 350. Okay. So the deadline for task 3 is 350. What we want to do is we want to see whether task 3 can actually complete within this time. We want to see whether task 3 can complete within this time. Okay. So let's look at it. So if I look at the timing periodic interval, you will see that task 1 has released 4 instances within the deadline. Correct? This is the first instance, second instance, third instance, and fourth instance. So before 340, before 350, task 1 has 4 instances. So when I say 4 instances, means it requires that amount of time. Correct? So task 1 requires this amount of time to complete all its activities. Okay. How about task 2? Task 2 has 1, 2, and the third instance has also been released. Correct. So it has released 3 instances of task 2. So I have 3 instances of task 2. This is for task 1, is for task 2. So the total amount of time consumed by task 1 and task 2 is 280. Okay, 280 is the total amount of time consumed by task 1 and task 2. Okay, within that deadline of 350. Okay, so how much time does task 3 require? Task 3 requires 100 units of time, correct, to actually compute and finish. So if I take 280 plus 100, this is the time required by task 3. Then I get 380, which is bigger than the deadline set by task 3, which is 350. Okay, so when I look at these numbers, okay, it seems that task 3 is not schedulable. Okay, because of the interference, because task 1 and task 2 is higher priority. So because of this interference from task 1 and task 2, it seems that task 3 is not schedulable within that deadline. So, but is that really the case? Okay, is that really the case? So let's look at exactly what is going to happen. Okay, so coming back to this timing over here. So at time t equals to 0, all the tasks are ready. Okay, so now let's look at it in a bit more detail. Okay, so we can see that task 1 will take 40 units of time. So from here to here, I will take 40 units of time. And immediately after that, since task 2 has also been launched, task 2 will take another 40 units of time. Correct. Now, after task 2 takes another 40 units of time, what happens? The next periodic interval of task 1 only happens at this, at time t equals to 100. And the next periodic interval of task 2 only happens at time t equals to 150. All right. So which means that the gap over here, which is 80 to 100, is actually a free slot. It's actually a free slot for task 3 to actually do some work. Okay, so task 3 can actually squeeze in some work while there is a gap here. Okay, so 20 units of time, it can actually do some work over here. Then the next instance of T1 comes. So again, you have another 40 over here. Okay, but this comes to 140. And the next instance of T2 only happens at 150. So I have another gap here, another 10 units of time gap over here. Okay, and the same thing. So when the next instance of T2 happens, I take 40 units of time. So it will be 190. So over here, 190. But the next instance of T1 happens at 200. Okay, because every 100. Alright, so I have another 10 units over here. Alright, and then after that, what happens? So I have another 40 over here. Okay, 40 units of computation, and then this is 240. Okay, and the next interval of task 2 happens when? So this is 150, so the next interval happens at 300. So from 240 to 300, I actually have a gap where task 1 is not using the CPU, task 2 is also not using the CPU. So I have another 60 units of time to actually use the CPU. Now, if I look at all of this, I actually have 100 units of time, which is what I need. Correct? I need 100 blocks of time for task 3 to complete before the deadline of 350, and I actually am able to do it. Okay, I am able to do it. Okay, when you look at it, okay, at all the gaps that you have. All right, so why is it that the earlier analysis just now makes us think otherwise? Right? In this earlier analysis, the numbers suggest that it's not possible, but when you go deeper into it, you actually see it's possible. All right. So what is the thing that we need to do now? Okay, the way we analyze. So what we need to do is, instead of just looking at the computation time across all the tasks for the whole deadline, we need to look at it at more points. Because previously what do we do? We just take the deadline, which is 350, and say, okay, based on this deadline, how many instances have already been released and how much time is needed. Okay, but what we need to do is we need to look at the instances at more points, and these more points are basically the periodic intervals. Okay, the periodic intervals of all the higher priority tasks, of all tasks. Okay, so when you look at it at the periodic intervals of all the various tasks, then you will get a better idea of when or whether this is even possible or not. Yeah, somebody has a question. Okay, so let's look at this. How do I add in more checkpoints? How do I analyze it? So what I need to do is I need to check at all the periodic intervals of all the various tasks. So 100. So for T1, it will be 100, 200, okay, and 300. And for task 2 is also 150 and 300. Okay, and this will be task 3. So I need to check at all these various points. And each of these points, what I need to do is I need to compute whether the total demand is less than or equal to the capacity. So the demand means the computational time that I need, and capacity is how much time has already elapsed. Okay, and then whether I see I am able to fulfill this requirement or not. Okay, so let's look at this. So the first thing that we look at is time t equals to 100. So at time t equals to 100, what do you have? You have one instance of task 1 and one instance of task 2. Okay, plus you also have task 3. All right, because at that point of time, you have task 1, task 2, task 3 all already launched, but each of them launched only one instance. Okay, so when you come back here, you can see clearly. Okay, so at time t equals to 100, which is here. Okay, so what do you have? You have one instance of task 1, one instance of task 2, and one instance of task 3. Okay, so since you have one instance of each of these tasks, the total computation time you will require is 180. Okay, but only 100 units of time have passed so far. Okay, so it is not possible to finish all 3 tasks by that 100 units of time. Correct? So we go to the next checkpoint, which is 150. Okay, which is the next periodic interval of task 2. In the next periodic interval of task 2, what happens? Okay, so you come back here, you see that at the point of 150, which is here, this is 100, this is 150. Okay, you will see that another instance of task 2 has launched. So another instance of task 1 has already launched. So this is 1, this is 2. Correct? And then another instance of task 2 is being launched. Okay, so come back here, So the task 1 has already been 2 instances, but there is still only 1 instance of task 1 and 1 instance of task 3. Okay, so come back here. So you can see that task 2 is only beginning to launch. Okay, so we don't count that in, but task 1 is already in the second instance. Task 2 is still only finishing up the first instance, haven't launched the second instance yet. And task 3 is still in the first instance. Okay, so the total computation time at that instance is 2 times 40 plus 40 plus 100. So again, the same thing, 220, but it's still bigger than the timing that you have. All right. And then you look at time t goes to 200. So you look at time t goes to 200, okay, which is here. Okay, so you'll see that this is the second instance of task 2. Okay, I'm still in the first instance of task 3, but second instance of task 2 is already launched, and the second instance of task 1 is also finishing up. Okay, so the total computation time is 2 of task 1, 2 of task 2, plus 1 of task 3. Okay, so the total computation time I require is 260, but it's still bigger than the time that is elapsed so far. Okay, and finally, when I check at 300, okay, when I check at 300 over here, okay, you will see that third instance of task 1 is launched. Task 2 is still only second instance, and task 3 is still first instance. Okay, so the task 1 is 3 instance, task 2 is 2 instance, and task 3 is 1 instance. And that adds up to 300, and the total amount of time is also 300. Okay, so you can see that when I check at more points, I will actually come to realize that at time t goes to 300, I'm actually able to schedule all the 3 tasks without any issue. Okay, so the issue why the earlier example calculation made us think that it's not possible is because we look at 350, and what happened at 350? By 350, another instance already launched. Okay, by 350, you already have a 4th instance of your task 1 and another 4th instance of your task 2. Okay, so because of that, you feel that it is not possible, correct? But actually, by 300, by time 3 goes to 300, you already are able to use all the gaps to finish up the requirements for task 3. So the task is definitely schedulable. This task set is schedulable by time t goes to 300. Okay, so that is basically the idea, right? That means we need to check more instances of time, all right, to do this and get a better idea. So how can we do it? Okay, so this is the mathematical approach. Okay, I will again go through the example. Okay, then I think it's easier to relate. So the easiest way to relate to this is you follow this formula here. Okay, what you do is at any point of time, that means when you take the computation of any periodic interval, whether it's 100, 200, 150, whatever, what you do is you take that time divided by the period. So if this is the time over the period, which is this, okay, multiply by the computational time required for that particular task, which is this. Okay, and then you add up. So the only variable over here is this t over here. Okay, so depending on which t you're looking at. Okay, so you'll be looking at 100 or 150, whatever. Okay, so you compute. Okay, and if you are able to look at the or get the answer where this timing requirement is within the deadline, that means W of 300 is less than or equal to 300. That means we can say that you are able to satisfy the requirement to schedule all these tasks by the time t equals to 300. Okay, so that is what this analysis does, which is taking the necessary and sufficient condition at the same time. Okay, that means if I'm able to find a time where this condition is fulfilled, all right, then I can say that the task set is schedulable. Okay, and the way you do this is very simply, you take the computation time multiplied by the time that you want to check over the period of that particular task. Okay, and you look at it for different timing instances. Okay, all the periodic timing intervals of all the higher priority tasks. And you will come across one where it fulfills, and then you say that yes, you satisfy the condition. Okay, so that is basically the way in which you can satisfy the necessary and sufficient condition at the same time. Okay, by doing this check. Okay, so don't worry about all the formula and all this theory part. As long as you can relate to how to apply it, okay, when you're looking at the number, then I think that is fine. Okay. Okay, so we just have a small part here, EDF, then we can go for a break. Okay, so this earliest deadline first scheduling. All right. What is earliest deadline first scheduling? So in this, until now, okay, when we look at the RMS algorithm and everything, we were talking about fixed priority. That means once we decide the priority, it is fixed. But earliest deadline first scheduling algorithm is dynamic priority. That means at any point of time, the priority will keep changing. Okay, so the priority changes based on the deadline of the task. So the task with the earliest deadline will have the highest priority. Okay, so let's look at this example. Okay, so let's look at these two tasks, T1 and T2. So when you look at these two tasks, you can see that since task 1 has the shorter period of 4, then task 1 will run first. So at the very first instance, task 1 will run. Okay, and then after that, task 2 will be able to run. So when task 2 is running, again, whenever a new periodic interval of any task comes, okay, then we will see whether the current task is higher priority or the new task is higher priority. Okay, so when you look at this, what do you see? You see that at this time t equals to 4, okay, what happens is another instance of T1 is about to launch. All right, so when T1 launches, okay, the deadline will be 4 units away, which is the time t equals to 8. Whereas for task 2, so task 2 hasn't finished, okay, because task 2 requires 5 units of time. Okay, task 2 hasn't finished, so it requires 5 units of time. But what happens is, since task 1 is also going to launch at time t equals to 4, okay, task 1 is considered higher priority. Okay, why is it higher priority? Because task 1's deadline is here, whereas task 2's deadline is here. Okay, at time t equals to 10. So at the point of instance where at time t equals to 4 and there's a new periodic instance of T1, okay, the task with the earlier deadline will get a higher priority. So since task 1's deadline would be at time t equals to 8 and task 2's deadline is time t equals to 10, so task 1 will be considered higher priority. So task 1 will take over and run first. Okay, then after that, your task 2 can carry on. Okay, but when task 2 carries on, it requires another 3 more units to complete. All right, but what happens is at time t equals to 8, okay, another instance of T1 will want to launch. Correct, but the moment the scheduler sees that T1 is going to launch, you will see that T1's deadline will be at time t equals to 12, whereas the T2's deadline is at time t equals to 10. So because of that, T2 is considered higher priority and T2 will continue to run. Okay, T2 will continue to run and then it will switch over to T1. And when T1 runs, okay, at time t equals to 10, which is the next periodic interval of task 2, again the same thing happens, correct? The scheduler will see that for T1, the deadline is at time t equals to 12 over here. Whereas for T2, the deadline will be at time t equals to 20 over here. So since the T1's deadline is earlier, T1 is considered higher priority, so T1 will run first. Then T2 can run. Okay, so when T2 runs, okay, and then at time t goes to 12, the next instance of T1 occurs. And when the next instance of T1 occurs, the scheduler will see that for T1, the deadline is at t equals to 16, whereas for T2, deadline is at t equals to 20. So T1 is higher priority, so T1 will preempt T2 and T1 will run. Okay, and after that, T2 will continue. Now, when at time t goes to 16, is what happens is you will see that both T1, okay, will launch, T1 will launch another instance, and T1 will have a deadline of 20. T2, which is running, already has a deadline of 20. So since both of them have the same deadline, then the priority is the same. And since the priority is the same, then they will both, then T2, which is already running, will just continue, and then T1 will run. Okay, so that is basically another type of scheduling algorithm called EDF. Okay, so this is called a dynamic scheduling algorithm. Okay, so there's a question why the third instance of T1 is not executed at T8. Okay, because at time t equals to 8, okay, at time t equals to 8, what happens is, okay, at time t equals to 8, okay, when the next T1 instance is launched, the deadline for T1 is 4 units away, which is at time t equals to 12. But the deadline for T2 is 2 units away at time t equals to 10. Okay, so since the deadline for T2 is earlier, then the T2 will carry on. And then only you will switch to T1. Okay, so this is what we call the dynamic priority. That means the priority will keep being reassigned based on which task has the earlier deadline. Okay, so this scheduling algorithm is called optimal scheduling policy. Okay, so similar to RMS, right? So for RMS, we say that it's a fixed priority scheduling policy. So if a feasible schedule exists for fixed priority scheduling, RMS will definitely be one of it. So similarly, if you're talking about dynamic priority scheduling, if such a schedule exists, then EDF will definitely be one of it. And EDF will always produce a feasible schedule if utilization is less than equal to 1. Alright, so that is the advantage of dynamic scheduling. That means I don't need to check anything else. As long as I fulfill this, I straight away say that it's necessary and sufficient. Okay, necessary and sufficient. I don't need to do any other check of utilization bound or checking the periodic intervals or nothing. Okay, as long as utilization is less than or equal to 1, I can straight away say that it is definitely schedulable. Okay, using a dynamic priority scheduling scheme. Okay, so I think now is a good time to take a break. All right. So we still have a few more slides. Okay, a bit on Watchdog timers, priority inversion, and so on. Okay, so we'll take a break now. It's 7:50. So we'll take about maybe 15 minutes break, 8:05 or 8:10, and then we'll come back. Okay, and then I will finish up the rest of the slides. Okay, and then I will spend some time talking about the assignment 2 and the term paper. Okay, so in the meantime, if you have any questions, you can just put it in the chat. Okay, when we come back, I will address those questions. Okay, so I'll see you back here in about 15 minutes time. Okay, so welcome back. So let's continue from where we left off. Okay, so coming back to our scheduling, correct? So when we talk about prioritize scheduling, okay, we understand that higher priority tasks will always take over the CPU, correct, and be able to run. Okay, and of course, one of the assumptions that we looked at, we took earlier, when we looked at all this analysis, is that there is no dependency, correct? The tasks are independent, alright, so the able to be analyzed separately. Now, in reality, of course, there is dependency, correct? In reality, there is dependency because the shared variables, shared resources, alright, that different tasks will need to get access to. Okay, so whenever you have shared resources, shared access, for example, a shared buffer. Okay, so we know that if I have a shared buffer between two tasks, correct? So if I have task 1 and task 2, and both of them want to access this same shared buffer, the way we should go about doing it is by using mutex. All right, so we have already seen that and understand how it works. So we need to lock and unlock, okay, before and after. All right, and once you acquire the lock, then next task is trying to lock will not get it and will go to a block state. Okay, so of course that works nicely, all right, in protecting this shared resource. But in terms of priority, it can cause an issue which is known as priority inversion. Now, what is priority inversion? Okay, so let me open up. Okay, so instead of going through those words, okay, that one you can read. Okay, so let me draw it out over here. So let's assume that we have task 1 and task 2 tasks. Okay, or we call it a high priority task and a low priority task. Okay, and this is the timeline. Okay, so let's assume that when the low priority task runs, okay, it runs, and at this point of time, it acquires a resource A. Okay, so it is running over here. It acquires a resource A. Okay, after it acquires resource A, it is still running. Okay, so until this point of time, we can say that the high priority task was probably in block state because of something else. All right, and suddenly at this point of time, okay, it becomes ready. Okay, and then there is a context switch. So the high priority task is not going to take over, it's going to run. Okay, and when it starts to run, it also wants to acquire resource A. Okay, but what is the issue? The issue is the resource A has already been acquired by the low priority task earlier on. Okay, so because of this, then the high priority task, when it tries to acquire resource A, it will not be able to get it. Okay, it will not be able to get it. And that means it has to go to a block state. Correct, it has to go to a block state. And when it goes to a block state, okay, let's assume that there is no other task. Then what happens? You come back here. Correct, you come back here and then your low priority task runs. Okay, until a point of time, okay, so the low priority task is going to run while the high priority task is going to be blocked. Okay, and then until a point of time where I release resource A, then you can say that the high priority task will be allocated the resource, and because it is a preemptive scheduler, automatically this task will get to run. Okay, now when you look at this whole scenario, what you observe that this period of time is a period of what we call a priority inversion. Why inversion? Because you have a high priority task blocked because of a low priority task. Okay, and this goes against the very nature of why we even want to have a priority driven scheduling algorithm, correct? The whole idea is the moment a high priority task is running, you should be able to acquire, or you should be able to run, correct, and execute. But because of this resource, okay, this issue becomes inverted, where a low priority task is able to take over the CPU and run while a high priority task is blocked. Okay, this is one scenario, but this scenario can get a lot worse. It can get a lot worse. Why? Because what if there is another medium priority task? Okay, and that medium priority task, okay, so if I take this away, and if I say that that medium priority task, okay, at some point of time here becomes ready. Okay, so until then it was blocked, and then at that point of time it became ready, and then it starts to run. Then what happened? It will run until a point of time when it releases or it gives up the CPU. Correct? And only when it gives up the CPU, then okay. So what I'm saying is that the medium priority task will actually get to run before the low priority task can release RA. So it is still holding on to RA. Low priority task is still holding on to RA, but before it can release the RA, the resource A, the medium priority task takes over, and then it starts to run. Okay, and until a point of time when it releases the processor, then the low priority task can run. Okay, and then when it runs, then it release, okay, RA, release the resource, the shared resource, and then finally, okay, and then finally your high priority task can run. So it gets RA and then it can run. So in this scenario, you can see that this period of priority inversion is a lot longer now. Okay, and this is only one medium task. Imagine that I have many other medium tasks, medium 1, medium 2, medium 3, and a lot of medium priority tasks that are going to preempt this low priority task before it can release the resource. Okay, so this is actually a very critical issue, correct? Because the very fact that you say that this task is high priority means it is doing something important, correct? But it is going to be blocked, okay, it can potentially be blocked for very, very long because of the low priority task holding the resource, which then gets preempted by other medium priority tasks. Okay, so if the high priority task is really doing something that is really mission critical, some safety related and so on, then it can cause a lot of catastrophic failure in the system. Okay, so it is an issue that we need to handle, correct? This priority inversion issue. Okay, and this is a serious issue. So how can we resolve this issue? Okay, so thankfully, all right, the OS itself has a built-in framework to solve this for us. Okay, without us having to do anything. All right, and that is basically what we call priority inheritance. Okay, priority inheritance. So let me explain what is priority inheritance. So in priority inheritance, what happens is the moment a high priority task like this gets blocked. Okay, so maybe let me redraw this over here. So I have a low priority task and a high priority task. Okay, so the same scenario, I will run and then I require resource A. Okay, and then I will get preempted over here. Okay, and then my A will run, high priority task will run. Okay, and then when I try to acquire resource A, I will fail. Correct. Now, what this priority inheritance mechanism does for us is, the moment a high priority task is blocked because of a low priority task, at this point of time, what happens is this low priority task will automatically be elevated to be temporarily high at the same level as the task that is blocked. Okay, so the moment the high priority task is blocked, what happens is this low priority task is considered to be equivalent to the high priority task in terms of the priority level. Okay, so this low will suddenly become high. So when that happens, okay, it will allow the low priority task to, by default, of course, once it's blocked, it will be allow it to run. But what more importantly it does is, even if there are other medium priority tasks here, medium 1, medium 2, and so on, they cannot take over this low priority task, because now this low priority is considered high priority. So this low priority task will be able to run until a point of time where it releases the RA. Okay, once it releases the resource, then we know that the high priority task will get the resource. We'll get RA, and then it can run. So the moment it releases the resource A, it will automatically come back down to the usual priority, the standard priority that it was originally having. Okay, so it's only that instance. So when this instance happens, when the high priority task is blocked, then the low priority task will consider to be high priority. It means the same level as the task that is currently blocked. But the moment I release the resource, I'll go back to the original priority that I had before. So this helps us to ensure that I do not get preempted and delayed any further by medium priority tasks. Okay, so there is still priority inversion. It's not that there is no priority inversion, but now we consider it as bounded. Okay, so over here, in this earlier case, we call this another term for this is what we call unbounded. Why is it unbounded? Because we do not know how many medium priority tasks there can be that will preempt the low priority tasks and continue to delay the high priority tasks. So it's unbounded. We can't predict. All right. But in the case of priority inheritance, now we say that this is considered bounded. This is considered bounded priority inversion. Okay, why is it bounded? Because I know that I will only be blocked until a point of time when this low priority task releases the resource. So anybody in between will not interfere. Okay, so that is the whole idea behind priority inheritance protocol, okay, which is what is mentioned here. Okay, so the lower priority task inherits the higher priority task priority for that duration until the resource is released. Okay, so the other variation to this, okay, so this is what we call priority inheritance protocol. Very short form, we call it PIP. The other one is priority ceiling protocol, which is PCP. Okay, so what is this PCP? How is PCP different? It will raise the priority the moment it acquires a shared resource. Okay, so coming back to the timing diagram, what is the difference? So in PCP, what happens is, in priority ceiling protocol, the moment I acquire resource A, and since resource A is shared between a low priority task and high priority task, I will immediately go to a high priority over here. Okay, the moment I acquire a shared resource, I'll go to high priority, and then subsequently when I release the resource, I'll go back to low priority. Okay, so in the priority inheritance, I only go to high priority if I am blocking somebody. Correct. So since the high priority task was blocked, then I change the priority. Okay, and then once it is unblocked, I release and come back to my normal priority. But in the priority ceiling protocol, I will raise to high priority the moment I acquire the resource. That means, for example, the moment I lock the mutex, I will straight away go up. Okay, and when I release the mutex, I will straight away go down. Okay, so again, this is just two different mechanisms that both help to sort of help us resolve this issue. And like I said, this is handled within the OS. So most OS allow some one or the other. So they might either implement priority inheritance or priority ceiling, and basically this helps us to minimize the impact of this priority inversion. Okay. Okay, so of course, besides that, there is also another potential issue, which is what we call the deadlock. Okay, so what is deadlock? So for example, I have two tasks, T1 and T2, both requiring two resources, R1 and R2. So let's assume that task 1 runs first. So when task 1 runs first, it goes and locks T1. Okay, and then after that, maybe it gives up the CPU, so task 2 runs. So when task 2 runs, it goes and locks resource 2. Okay, so task 1, okay, has acquired resource 1, and over here, task 2 has acquired resource 2. But the thing is, task 1 requires both of them, and task 2 also requires both of them. Okay, so what happens is, first task 2 locks resource 2, but when task 2 tries to lock resource 1, what happens? It gets blocked. Okay, because resource 1 is already locked, correct? So because it is locked by task 1, it goes to a block state, and if there is no other task, let's say I switch back to task 1, and when task 1 is running, it tries to lock resource 2. Okay, and then it realizes that resource 2 is not available, so it tries to acquire resource 2, but again it's not available because task 2 this is task 1. So task 2 already acquired resource 2, so it's not available, so it also goes to a block state. So what happens? Both of them get blocked indefinitely, waiting for the other person to release, but the other person cannot release because it cannot run. Correct? They're both blocked. Okay, so that is what we call a deadlock situation. Okay, where tasks are waiting for each other to release the resource, but nobody is able to run, so nobody is able to release the resource. Okay, so this is of course another potential issue. Okay, in this kind of multi-threaded code. Okay, so of course, one good thing is over the years, development tools, okay, software development tools that we use have already been quite advanced, that they can sort of analyze software and sometimes even detect potential deadlock situations, okay, and give us some warning upfront. Okay, so it is good. Okay, so development stage it is possible, but of course it is still the programmer's responsibility to manage resources correctly. Okay, so of course, what are the ways in which we can prevent deadlock is one easy way is ensure that everybody acquires resources in the same order. Okay, so if I have task 1 and I have task 2, and both of them require resource 1 and resource 2, then everybody must follow the order. So if task 1 is running first, it must always try to acquire resource 1 first, then resource 2. So if after it acquires resource 1, it gets preempted and task 2 starts to run, if it tries to acquire resource 1, it will immediately get blocked. Okay, and then it will be allowing task 1 to continue, get resource 2, and then proceed. Okay, so if everybody acquires resources in the same order, that itself is a way of preventing deadlock. Okay, but of course this may not necessarily be practical in all cases. okay, or convenient. So another way is you can always have some sort of timing timeout sort of a mechanism where if you cannot acquire all the resources within a certain time, then you release all the resources and try to start over again. Okay, so again, all this requires further thinking and some practical thought about how you want to implement it in your code. Okay, but again, the simplest way is just ensure that everybody acquires resources in the same order. So that ensures that whoever gets the first resource is more or less going to continue and finish up before the next person gets the resources. Okay, then another thing is cases where your system is running, okay, but it reaches a point of time where it can no longer continue to run. That means it reaches a point of failure, okay, where it is not able to continue. Okay, just like how I think maybe nowadays not so often, but in the past where your computers or laptops you will use and suddenly you see that blue screen, correct, and the whole thing just reboots. Okay, even the smartphones, I think many years back, the earlier phones used to have these issues more often. I think now it's a lot better. Correct, but it still happens once a while, correct, where suddenly everything just jams up and you can't use your device and then you see it just reboots by itself. Okay, so how is it able to do that? Okay, what causes it to reboot by itself? That is basically what we call the work of what you call a watchdog timer. Okay, so what is a watchdog timer? It is basically a built-in mechanism. Okay, it's more of a hardware design, okay, within the system that allows you or allows the system to detect any major failure such that you can't even execute code correctly anymore. Okay, so how a watchdog timer works is basically a hardware counter that is designed to count down to 0. Okay, so you start off at some value. So let's assume a simple value FFFF, and you're supposed to go all the way down to 0. But the idea is you should not reach 0. Okay, so there will always be this interrupt that runs that will periodically, okay, come in to reset it back. Okay, so whenever the interrupt comes in, I'll go and reset back the timer to the top. Okay, so the idea is if I'm able to execute interrupt, I'm able to execute the code, then there is still some functionality of the system. But if I'm not able to process interrupt, I'm not able to execute any code, then this watchdog timer will count down all the way to 0. And if it ever does that, then we know that the system has really failed. Okay, the system has really failed. And then what we will do is this in the hardware is automatically tied to the reset pin of your system. Okay, and will cause the system to reboot. Okay, so this is again is not something that is in the software. Okay, though the timer configuration all is just some basic setup, but it's more of a hardware driven solution. Okay, almost all devices will have this capability, so that in the event where there is a major failure and the system cannot recover, then you can use watchdog timers as a way to reboot the system and start over again. Okay, so next is this concept of re-entrant function. So this is also another important thing that you must consider. Okay, so what is a re-entrant function? Okay, so when you have two tasks, okay, thread A and thread B, okay, they may both require some similar library code. Okay, so maybe both of them are doing some signal processing. Okay, thread A is doing a different type of signal processing, thread B is doing a different type of signal processing, but maybe a common part of the algorithm is maybe you need to do some shift and multiply. Okay, so most signal processing have a shift and multiply block. Okay, so let's assume that maybe this shift and multiply is a common function that both thread A and thread B must use. Okay, so if both of them are using a common function, then it could be that while I was in the midst of this function, I got preempted. Okay, so thread A was running this function, but before I could finish, I got preempted and thread B is running, and thread B also calls this function. So it is a common function that two different threads are calling. Okay, so how can I make sure it is safe? All right, so in order for us to make sure it is safe, we must make sure that it uses thread specific instances of data that is not shared. And basically what it means is you only use what we call automatic variables. Okay, if you're not sure what is automatic, it's basically variables that you create within the function and you do not have any static or global variables. Okay, if I have a function A and I have a variable integer x, y, z, okay, then this x, y, z is considered automatic variable. Why? Because they are created on the stack when I call function A. Once I exit function A, x, y, z is no longer there. Okay, so if I call function A from task A, okay, it will create x, y, z on the stack space of task A. Okay, and if I get preempted, it's fine, because if task B calls the same function A, the x, y, z will be on the stack space of task B. Okay, so it is what we call automatic variables. That means they are created within the scope of that context, within the scope of that particular task. Okay, whereas if I have global variables, integer x, y, z, okay, these are global variables, then there is an issue. Okay, because global variables means that task A, if you use x, y, z, then task B will also reference the exact same x, y, z. Then you have data corruption and all these issues coming in. Okay, so if you have any functions, a shared library code between multiple tasks, then in order to make them thread safe, okay, we need to make sure they are what we call re-entrant. So the easiest way to ensure that re-entrant is you do not use any form of static or global variables. You use only thread specific variables. Okay, so let's just look at some case studies. All right, so I mean we have covered quite a bit of the OS and the things. So let's look at some popular case studies about OS systems in the past. So this is on the space probe. This is 1994. All right. So in this case study, what happened was this space probe was supposed to be doing a lot of experiments and collecting soil samples and things like that. Okay, well, what happened was a software exception occurred, causing the thruster to fire for 11 minutes straight. Okay, and then it depleted most of the fuel. Okay, because once it started burning up that thruster, it caused the probe to rotate at a very high speed. Okay, but by the time they were able to reboot the system and get it back into control, it was too late, okay, to successfully complete the mission because of too much of fuel being depleted. Okay, so another one was this Mars Pathfinder 997. So this was a classic case of a priority inversion problem where a high priority task, which was a communication task, okay, was forced to wait on a mutex held by a low priority science task. Okay, so this science task is basically the experiment that the rover was supposed to carry out on Mars. Okay, so because of some, again, software design with the mutex, the communication task was forced to wait, okay, whenever it was supposed to do some experiments. Okay, and because of this timing issues, okay, the system again wasn't stable, and the Watchdog timer was able to reboot the system. Okay, again, after a reboot, it was fine, but they know that there was another potential case for the issue to resurface. So before that, they were able to quickly upload a new code and fix the problem. Okay, so again, because of that quick updating of the code, they were able to salvage the mission and complete it successfully. Okay, another case, which is the Patriot missile bug. Okay, so if this is a classic case of what I would say a designer or an engineer and not understanding the communication that is conveyed to the end user. All right. So in this classic case, what happened was this Operation Desert Shield, okay, where the US deployed this Patriot missile system. Okay, and basically what it will do is it will use the velocity of its target and the current time to predict where the missile will land. Okay, so whenever that a missile was detected, all right, it will predict, okay, where it will land to decide whether you should take any action or you would ignore the missile. All right. So of course, there was some bug, all right, in the system where the internal clock would drift over time. Okay, so there will be some drift that occurs over time. So of course, I mean, this was known. Okay, so this bug was not a sudden thing that they realized. It was known, but what happened was the soldiers were just told that you just need to regularly reboot the system so that the drift would not be so bad. Okay, so every time you reboot, you go back to zero drift and then you start again. Okay, but again, because this term regular was left for interpretation, they did not know what it meant. Okay, and then they left the system on for more than 100 hours. Okay, and because of that huge time, the drift became quite large, up to 0.34 seconds. Okay, so of course 0.34 seconds is a very big amount when you consider the speed of a missile. Correct. And what happened was a missile that was incoming was miscalculated to land in an open field, but in fact it landed in the US airfield. Okay, so this is again, like I said, a communication issue, right? Because from the engineer perspective, you say, okay, I just regularly reboot the system, but actually you should be more specific, correct? You reboot the system after how many hours of usage or something, or if not, you put it in the software itself that after a certain number of hours, the system just reboots by itself, okay, without the user having an option. Okay, so that sort of sums up all the top things we wanted to discuss for this topic. Okay, so we talked about RMS, EDF, priority inversion, and so on. Okay, so that is all good for this. All right, so this is the second last topic, okay, on the for the module, okay, on the OS part. Okay, so before we move on to discuss of the so let's talk about the final exam first. Okay, so the final exam will be physical face-to-face exam. Okay, so it will not be luminous quiz or anything. It will be face-to-face exam. Okay, as per exam schedule. Okay, so if you're not sure your exam schedule, you can check. Luminous also has the exam schedule. Okay, for each module. Okay, so every module, if you go to Luminous, there will be an exam date and time written there. Okay, so open book exam. Okay, so only hard copy material is allowed. Okay, so all chapters will be covered. Okay, format will be MCQ plus short answer questions. Okay, so the MCQ part is only the first half. That means the MIPS part. So the analysis of code is for both, because the MIPS part you need to maybe analyze some assembly language code and then understand what's happening. The writing of code is strictly for the OS part only. Okay, so analysis and writing of code you have both for OS. Okay, but for analysis, is only the MIPS part. Okay, so you won't have to write any assembly language code, but you need to analyze assembly language code because that will be part of the MCQ questions. Okay. So I'll come back to this again next week also, just to recap. Okay, so again it's face to face. So it is again this is the direction given by scale. Okay, they want to move everything back to face assessments. Okay, so that is why this is face to face. So please follow the schedule. Yeah, it's face to face means paper, pen, exam, the usual one. All right, so I think, yeah, so that is basically the direction from NUS, all right, that they want to move everything back as much as possible to how it used to be. Okay, so we are going back as face-to-face exam. Okay, that means pen and paper. So no laptop, no computer. It's open book, so you can bring in any material you want. Okay, for the exam. Okay, so again, yeah, you have questions you can ask. Yeah, any amount of materials you can bring. Okay, but I think the more material you bring, the more confused you might get. Right, so probably good to bring in the right amount of material that you think is sufficient. You don't want to spend all your time flipping through all your material to find something. Right, you just want to bring in the right amount so you know what is where and easy for you to do it. Okay, so yeah, if you have other questions, you can still ask. Okay, so let me come back to the midterm, the assignment and the term paper. Okay, so let me first talk about the term paper first. Okay, so for term paper, basically again you are designing a processor, okay, which is 18-bit instruction length. Okay, so from the MIPS, okay, so for MIPS we know that is 32-bit. So from 32-bit, when you cut down to 18 bits, definitely you are losing some of the registers, some of the flexibility and so on. Okay, so up to you to decide, okay, how you want to break up these 18 bits. Okay, so if you decide to say I want 3 bits for registers, then you have 8 registers. Okay, if you have 3 bits for registers, then you have 2 to the power of 3, which is 8 registers. Okay, so if you have 8 registers, then you just can call them with your own name. So you don't need to follow MIPS naming convention. Okay, so you can just say that, okay, these registers, I'll call them R0 to R7. Okay, register 0 to register 7, up to you. Okay, you don't need to follow like how MIPS was saying, okay, I have A0, S0, T0, no. You can just use whatever naming convention you like. Okay, then if you say that I set aside 4 bits for opcode, for example. Okay, I'm just giving you examples, right? Don't take it as right or wrong. So it's up to you to decide. So if I have 4 bits, then I have 16 instructions. If I have 3 bits, then I got 8 instructions, up to me, correct? Now, how many instructions do you need? You need enough instructions to do what you are supposed to do, which is compute the square of a variable n stored in memory, correct? So the idea is I have a variable n stored in memory. I need to be able to read that data, bring it to my processor, compute n squared, and write back. Okay, so I need to do this. So I need to write some assembly language code to do this. Okay, so depending on the instructions that I support, I must make sure that whatever instructions I support, I'm able to fulfill this. Okay, so you don't need to think about all the instructions that MIPS has, all the instructions that we have covered. You focus on what instructions do I need to support in order to fulfill the requirements. Okay, of course, if you have more than enough, then you can add in more instructions. But the bare minimum is you have enough instruction to support this. Right, that means this requirement. Okay, and in the report, again, follow the guidelines given in terms of the number of pages and all of that. All right, so again, I don't want you to write a very lengthy report. Okay, so it's just follow that limit that is given. So you just come directly to the point to explain what is it, what is your design, what are the decisions you have made, and how your processor works, and things like that. Okay, so that is the term paper part. Okay, so I think we have covered this quite a few times. All right, but if you still have questions, you can still contact me. Okay, the next is the assignment 2. Okay, so for assignment 2, basically you're supposed to design a calculator, correct? Where you are supposed to break it up into minimum 3 tasks. Okay, so you have 3 tasks: task input, okay, task compute, and task result display or something like that. Okay, so what you need to do, so in the user interface, you must be that, okay, for example, if I want to do 5 plus 2, okay, so the first thing is I must say enter first number, right? Enter number 1, then you capture 5, all right, and then you enter the operation. Okay, then you can decide how you want to capture, right? You can say 1 is, you can have a menu for the user, all right, and say maybe 1 is plus, 2 is minus, whatever. Okay, so if I say 1 is plus, 2 is minus, something like that. Okay, so you can decide a menu. Then for example, I say 1, so it's plus. Then enter number 2. Okay, then I say 2. Then you print out the result. 7. Okay, so the key thing is you must break up this into the 3 tasks. Okay, so the first, you can see the first task input must run. I must capture the num1. Okay, so no, this is task task op. Yeah, task op. Capture the operation. So after I capture the num1, I must be able to switch over to task op. So when task op runs, so all the while is waiting, then task op runs, you will capture the operation. All right, once I capture the operation, I must be able to go back and I must be able to capture num2. Okay, so I was able to run and capture num2. And finally, after I capture num2, I must be able to compute. So it's up to, so I compute and then send it to task result. Okay, so task result will be able to take it and do a print. Okay, wait, let me just check my document again, whether the compute is done where. Okay, so yeah, so you can, it's not specified where you should do the final computation. So you can do it in the input or you can do it in the result. Okay, so this compute, you can do it in task input or you can pass it to task result. Also, it's up to you. Okay, so basically you need to have this switching of tasks and this various action carried out. And how you can do this is by leveraging on the example code I already given you. So I already passed you the code for the task queue and a message queue. Okay, and we've already covered this concept last week, okay, on how you can synchronize, okay, and at the same time pass data from one task to another task. Okay, so it's up to you what you want to use, whether you want to use task queue or you want to use message queue, it's up to you. Okay, so using the sample code, all right, you can just build upon that and then extend it to perform this action here. Okay, so as long as you follow the requirement, that means I split it to 3 tasks and I follow the sequence of getting the first number, then operation second number, and then pass it to a third one for printing of result, then it's more or less there already. Okay, so you don't need to work from scratch, correct? I already gave you the sample code for the task queue and message queue, so you just choose one of it and you just extend from there. Okay, so that is let me see any okay, num2 must be captured only in the number must only be captured in the task input. Task op is only to capture the operation. Okay, so if you're not very sure, again go back to last week's lecture recording. Okay, have a look at the demo that I did on the task queue and message queue. Okay, so I think once you understand that code, how it works, then it should be quite manageable to extend it to this. Okay, yeah, so that's all we have for today. So next week we have one more lecture. On the virtual memory. Okay, and then after that we have the final tutorial. Okay, and then we will, with that we can wrap up the module. Okay, yeah, so I think that's all I have. So those of you who have questions, you can stay behind, all right, and we can discuss. If not, thank you, good night, and I will see you all next week. Okay, what is the deadline of assignment 2? Let me just check. I think you can just see the folder closing date. Let me just check. Okay, assignment 2. Okay, I haven't put in the assignment 2 submission folder yet. Okay, so the submission is the last week. That means the week 13. Okay, I will update the okay, let me just confirm again. So it will be the last week. The last week is week 13, which is the April 13 to April 17. 13 to 17. So it will be the last week, that Friday. Yeah, that means, yeah, you're correct. 11 to 15, sorry. 11 to 15. Okay, if I'm not wrong, that 15 is a Good Friday. Okay, it's a holiday. Okay, yeah, so I will create the submission folder and I will send an announcement on it. Okay, so if any questions, you can stay back and ask. If not, yeah, so next week we will have our the final chapter on the virtual memory.
For the final exams, right, the writing code part OS is analysis on OS code.
Yes, you
Okay.
need to write some short pieces of code for the OS and also analyze some OS code.
So we have to refer to the labs to know more about the OS code.
Yeah, I mean, if you understand the three, so basically we gone through three sets of code. The first example, and then the message queue. First one was on the semaphore, then message queue and task queue. So if you understand how those code work, then I think should be no issue.
Okay, thank you.
Looks like no other questions. Okay, so thank you. I'll see you all next week. Okay, bye.